Okay, we're good.
All right, so thank you everyone for coming to the Graphs and Matroids seminar. Today our speaker is Charles Semple, who will be telling us about matroids with wheel and whirl-like properties.
Thanks, Rose. So this is a talk accumulation of various sources and various parts, and their names will pop up as we go through it. So the question I'm asking, sort of a first up question, is what are the matroids, for example, where every element's in a 3-circuit or 3 co-circuit? You might be able to guess the answer straight away. Or you can even ask something simpler. If I get this, better just change this around a little bit. What about every element's in a 2-circuit or a 2 co-circuit? All right, so for example, the first one, you can just take direct sums of U1, 2. And every element's in a 2-circuit and a 2 co-circuit. In fact, you might like to think if there are any others, but it doesn't, you can quickly realise there's not. What about a 3-circuit and a 3 co-circuit? Well, we have touched wheels and wheels theorem for that one. And so the original theorem stated that if you're a 3-connected matroid, then every element E of M, neither the deletion or the contraction is 3-connected, if and only if rank at least 3 and you're isomorphic to a wheel or a whirl. That's how it's usually stated, but an equivalent statement is the corollary. Okay, and it says that every element's in a 3-circuit or a co-circuit, if and only if you have rank at least 3 and you're a wheel or a whirl. Okay, so effectively for 3-connected matroids, that answers the second question about 3 circuits and 3 co-circuits, and in fact turns out they're the only ones, are wheels and whirls. So they're the sort of questions that sort of prompted this bit of work. But you may ask various other things, all right, for things that are less straightforward. So you might ask the question, what's the matroids with the property that every element's in a 4-circuit and a 4 co-circuit? All right, so for something like that, you might have pretty graph theorists in the audience. You could take a grid, all right, and every edge, in this case, is in a circuit, and every edge is in a 4 co-circuit. If I was to extend that grid and put it on a torus, all right, wrap it around a torus, all right. But that's a little bit wild, that class. The second class, so that you can think of other things as well. For example, you could have matroidally, you could have spikes. I'll say more what they are because spikes are going to arise several times in this talk. All right, so you think about taking freely, in this case, here's a rank 4 spike, 4 co-punctual lines. So I'll do that freely, but then I'll place the points on those lines, and they're not necessarily freely placed, other than that, they're not in parallel, and they don't meet at the pointy end, and that's a spike. All right, and they also have the property that every pair of elements in a 4-circuit. So here's a pair of elements, and here's a 4-circuit they're in. All right, and here's a 4 co-circuit they're in, and it just happens to be the same set. All right. So there's a couple of questions. Here's some more questions. What about every element's in a 3-circuit and a 4 co-circuit? I don't know the answer to that one, just like I don't know the answer to the first one. Or what about rather than just asking every element, what about if you ask every pair of elements? So if every pair of elements in a 4-circuit and every element's in a 3 co-circuit, what could arise in that case? Or what about if every pair of elements in a 4-circuit and every element's in a 4 co-circuit? What could arise in that case? And you might like to think of examples that you may think of that arise. And more generally, you could ask the question, what about if every T element subset's in an L circuit and an L co-circuit? I should say here, if I'm saying an L circuit, I mean L element circuit. If I say an L co-circuit, it's an L element co-circuit. So I should have said that at the beginning. And you could do, and of course, you could vary it, so you could have extra parameter there. You could have every S element sets in an L circuit and every T element sets in an M co-circuit. Right, so you can vary the questions you might ask. And you'd like to think that if you've got a slightly enough constraints, you need a little bit of constraining on this problem, that you might just get a single family. All right, if you're sufficiently large. I mean, that would be the hope with all these sort of problems, that you just get a single class or just a couple of families if you're sufficiently large. Once you rise above the small examples that sort of, you know, can weave their magic ways and sneak in when you don't want them to sneak in. So they're the sort of questions we're asking. And so what we're going to look at first is this one, and this one. We're going to look at those four, all right? So I know a bit about those four. The other two I haven't circled, I don't know anything about, other than I can give you some sporadic examples and some generic examples as well, okay, that fall in those classes. So a student of Jeff Whittle's master's student, showed that for the second question I had, if M is in a 4 circuit and a 4 every pair of elements, I should say that, if every pair of elements is in a 4 circuit and a 4 co-circuit, then M is a spike. All right, provided you're sufficiently large, but sufficiently large is not that big in this case, it's only 13. It's only 13 elements. So just going to there. So here's the definition of a spike, but you can either, I'll say this definition because it's going to arise in a more general format soon. So if you've got a rank R spike, it's on 2R elements whose ground set can be partitioned into pairs, such that the union of any pair, so these are my pairs I'm drawing now, and the union of any pair is a circuit and a co-circuit. Or, as I said a couple of slides back, take, in this case, this is rank 5. Yep. Is that rank 5? It is, yep. Take 5 copunctual lines, all right, freely placed in rank 5, and then add 2 elements, pair of elements on each of those lines, but they're not necessarily freely placed. All right. You do get small examples. What if M's less than 13? You get examples like what's called R6, just 2 3-point lines freely placed, every pair of elements in a circuit and a co-circuit, and you even get things like K3. 3. Oops, one more line. And they also have the property that every element's in a circuit. The co-circuit one's a little bit, I don't know, that's more difficult to see, but if there are a pair of line edges intersecting at a point, at a vertex, then if I want to find, I should say, for the non-matroid theorist, a co-circuit graphically is a minimal set of, a cut set that's minimal with that property. And if I want to find a cut set or a bond minimal with that property, I could add those 2 edges to it as well. Right. And so there's a 4 circuit, a 4 co-circuit. So that, in some sense, that was the starting point for me in this work, was that paper, thesis of Joe Miller's. And then must be, I don't know, a few years ago now, James, Jeff and I were working together and we talked about trying to see if we could generalize this. Bit of a side problem from the stuff that Nick's been talking about a couple of weeks ago. And we considered this problem. So this time I'm asking for every pair of elements in a 4 circuit. So every pair of elements in a 4 circuit and every element in a 3 co-circuit. All right. So same sort of thing like the previous example. If you got at most 8 elements, then you get one of these sporadic guys. So if I did U35, probably the simplest example there. But every pair of elements is certainly in a 4 circuit. wrong colour. And every element's in a 3 co-circuit. So if I take that little there, then there's a co-circuit to go with it. All right. But what happens more generically if m's at least 9, and it turns out if m's at least 9, oops, whoa, get rid of that line. You get K3n for some n. All right. So in this case, every pair of elements in a 4 circuit, every element's in a 3 co-circuit because every element's instant with a vertex. In this case, every edge is instant with a vertex of degree 3. All right. And that's the generic case for that particular problem. So there it is there. So I'll give you a moment to have a look at that. So the 3 connected condition on it, well, it's to avoid things like, it's to avoid it so that no 3 element subsets of 3 circuit and 3 co-circuit. So here's another example that would fall in that class, but it's not 3 connected. Yeah, each of those points is joined on with the 2 sum, and each of the 3-point lines is both a circuit and a co-circuit. All right. So that there is both a 3 circuit and a co-circuit. So it just avoids that situation. The proof of that result it's not that long. For that one particular one, it's not that long. All right. From memory, you try and break up the elements so you partition the edge set so it falls into blocks of 3 co-circuits. So sets of size 3. So you partition the edges that way, and you get the property that any of the matroid induced by any 2 of those blocks is actually the cycle matroid of K23. All right, so you partition the set into 3 element co-circuits, and then any pair of them induces the cycle matroid of K23. Right, and that's effectively how it goes. And you can do that for provided at least 9, and then of course you get these sporadic examples as at most 8. The second one we're going to do is a variation on that one, but this time you've got every pair of elements in a 4 circuit, so we'll keep that, but every element's going to be in a 4 co-circuit. Okay, so now we're going to do that one. So this time the cutoff mark's at 15 rather than 8. All right, so every pair of elements M is in a 4 circuit and every element's in a 4 co-circuit. If and only if you have at most 15 elements, then you get one of 35 matroids, and I'll say what they are shortly. Just give a flavour of the matroids that arise. Or can anyone think what the generic example would be, given the result of the previous one? This is Oxy's tactic of, you throw a question out to the audience and no one responds.
Is it K4n?
Yeah. Thank you. And it's K4n for some n greater than or equal to 4. All right. So just as with the previous one, this arises. All right, every pair of edges is in a 4 circuit or a 4 cycle, and every edge is in a 4 co-circuit because every edge is instant with a vertex of degree 4. I can just delete those 4 edges in for that vertex, and that gives me my 4 co-circuit. The proof for this, for getting at least 16, takes a bit more work than the previous one, and that's because the flexibility of 4 co-circuits, but do exactly the same approach, just requires a little bit more work. Getting this part of it is the worst part of the lot, right? I remember visiting James, and Simon was working on it. I remember going to one of those. If you've ever been to Lockett Hall, they've got some beautiful offices and rooms to work in at Lockett Hall at Louisiana State University. They're all enclosed, no windows. You don't see daylight for the entire day, and you work in these rooms. I imagine they do have pretty good whiteboards, but I remember walking in, and Simon had up 4 co-circuits, I don't know, on every wall, plastered across the things, and it just looked like chaos. All right, absolute chaos. I remember going through this, and we must set there. We did several days trying to do the case analysis. I'm just pleased that Simon ended up writing up the case analysis for his thesis, and it wasn't me. Yeah, it was a little bit of a nightmare case analysis for it. So what the sort of matroids that arise of the ones with most 15? Well, most of them are paving, rank 4 paving matroids. All right, that arise. R10, which some of you will be familiar with, and a 12 element and a 14 element one. And so they got it quite large. The one thing I can say about the 12 element and the 14 element is that they're both representable over G of 4. All right. I don't know anything else about those 2 matroids, so I don't know whether they're connected to anything else. All right. The 4 connectivity condition, similar to the previous one, but this time I have to draw what they call a paddle. So you might think you don't know what a paddle is, doesn't really matter, but well, it does matter, I suppose, in some sense. But it's a book. Just enclose the book around it so that the covers of the book are joined together, so the pages are flipped out. And then what I'm going to do is each page or paddle of the book is going to have 4 points placed on it. Right, and then I have the property, and I do that for the other pages at the back, and every pair of elements in a 4 circuit, and every element in a 4 co-circuit. Right, so I'm avoiding situations like that. If it's, I don't know what the 3 connected examples are for this. All right, I don't know what the 3 connected examples are. Is there going to be more than one family? Yes, there will be, obviously. How many or how wild it is, I don't know. I don't know the answer to that. Right, so the next thing to look at, what about, so rather than just picking, so anyway, so I should say how the next bit of work came about. So a couple of years ago, we went to, probably it's more than that, but it's pre-COVID times. We had a workshop in Creswick, which is in Victoria, some 100 and something rather k's from Melbourne. And we were thinking about problems to work on. And so we thought about having more generic problems along these lines, where we're not fixing so much the size of the 4 circuit with 4 co-circuits. So what sort of thing can we say in general? All right. And one particular group there, which actually I wasn't involved in, I'll say who they were involved in, considered this problem. So what about it? So a matrix has the TL property if every T element subset is an L circuit and an L co-circuit. What can you say in that situation? So T and L are parameters, and say something a bit more generic than what we've just been talking about. So for example, wheels and wheels have the 1-3 property. Every element's in a 3 circuit, and every element's in a 3-element co-circuit. Right? Spikes have the 2-4 property. So every pair of elements in a circuit, and every pair of elements in a co-circuit. Can you say something a bit more generic about these things? Some general properties. Well, the first thing you can say is Nick Patel and Rutger Campbell, Deborah Chun, Kevin Grace, and Jeff Whittle showed that if L is strictly less than 2T, then there's a finite number of matroids having this TL property. All right, so there's a finite number of matroids having the TL property. So those don't apply there. These two examples here don't apply. Because L is not less than 2t, strictly less than 2t in this case. But U24, for example, has the 2,3 property. And there you go, proof by example. It's the only matroid with the 2,3 property. All right. So I'm sure their proof's a bit more elaborate than that, proof by example, but there's, you know, there is something with the 2,3 property, but U24 is the only matroid with it. So what about generic families? So what they looked at in particular was T-element subsets that are in a 2T circuit and a 2T co-circuit. All right, so if T equals 1, then this is the class of taking direct sums of U1, 2. So we've already seen that. All right, every one element set is in a 2 circuit, and every one element set is in a 2 co-circuit. So that's taking direct sums of U1, 2. And that is the class. That's what the class consists of. What about if T equals 2? Well, then the class contains spikes. All right, the class contains spikes. And in fact, more generically, it turns out that not only the class contains spikes, but if you're sufficiently large, that's what the theorem is going to come up to in a minute, then you're a generalization of a spike. So a T spike is a matroid whose ground set can be partitioned into pairs such that the union of any T pairs is a 2T circuit and a 2T co-circuit. So for example, if you're a 2 spike, ordinary spikes are a 2 spike. I can partition into pairs, and the union of any 2 pairs is a 4 circuit and a 4 co-circuit. So I'll just draw that again, just to remind those who's familiar. Right. And what are the pairs in this case? The pairs, the legs of the, here's my pairs. Right. And if I take any 2 of those pairs, they're in a 4 circuit and a 4 co-circuit. Right. And what the same group of people showed is that provided you're sufficiently large, so it's some function dependent on T, M has the 2T property if and only if M is a T spike. Right. So if and only if M is a T spike. I was going to say there's something else. There was something I was going to mention there, but it'll come back to me soon. If T equals 2, what does sufficiently large mean? It's at least 13. All right, and that was Miller's result from earlier. All right. What it is for other values of T, we don't know. The bounds I try to get, the Ramsey type bounds, they weren't particularly helpful. All right. So if an interesting problem to see what sort of lower bounds could you get on the sufficiently large part. All right. They made absolutely no attempt to try and do anything on that. All right. They use Ramsey type arguments, and so at the moment they're astronomically huge. So any bit of leverage on that would be interesting. Right. So these things, these T spikes, all right, they turn out to be highly structured. All right. So for example, they're 2T minus 1 connected. They have no 2T minus 1 circuits or co-circuits. All right, for example. And so they're interesting objects in their own rights. And that led, so in some sense, these are interesting, just curious problems to ask these sort of questions. But in terms of chain theorems and connectivity, quite quite questions. There's no reason to suspect that actually these T-spikes aren't going to rise and be crucial in the same way you've got wheels and whirls. So here's a theorem of Alan Williams, who was a student of Jeff's in 2015, it appears in his PhD thesis. If M is a 3-connected matrix with at least 13 elements, and M has no triangles or triads, and for every pair of elements, so every pair, neither their deletion or the contraction is 3-connected, then that's saying you must be a spike. And spikes are the only ones with that property, with those properties, right? Touch wheels and whirls theorem said, I don't need the condition on anything smaller circuits or co-circuits, but if I'm 3-connected, every element, neither their deletion or its contraction is 3-connected, then you must be able to whirl or whirl. All right. So if you think about how important wheels and whirls have been, there's no spikes in this context for pairs of elements is important. And so, so why not about T-spikes? Well, T-spikes are 2T minus 1 connected. All right, if T was 2, then I'm 3 connected. They have no 2T minus 1 circuits or 2T minus 1 co-circuits. And for every T element subset, neither the deletion nor the contraction is T plus 1 connected. All right, so T-spikes have those properties. And so Rattel et al. Established those properties in that paper, the same paper those previous results are in. And so you can ask their conjecture, and I presume it's still open, but given the fact that several of the people will be in the audience, they'll be able to tell me whether it's not, but I'm pretty sure it is. If M's a 2T minus 1 connected matroid with no 2T minus 1 circuits and co-circuits, then if you're sufficiently large, either there's an element, a T element subset you can delete or contract and stay T plus 1 connected, or you're a T-spike. Right. Or you're a T-spike. All right, so I'll ask Nick. Nick will be in the audience. Is that still open, Nick?
Still open.
Yeah. Obviously, there's no counterexample or anything like that to it.
That we know of.
No. It's time. All right. So I'll leave that for that particular problem about looking at every T element sets in an L circuit or an L co-circuit, or you can vary it how you want. Let's go back to touch wheels and whirls theorem, and let's take other direction on this problem. So the corollary of touch wheels and whirls theorem is, it's corollary, but 3 connected, every element's in a 3 circuit and a 3 co-circuit, if and only if you're a wheel or a whirl. But actually, wheels and whirls have stronger properties than that. So here's a 5 wheel, and I'll label it. I don't think I need label. I'll label it. And I'll label it in that way. You might observe the way I label it in some sort of circular way. And then if I put them in a circular ordering, what do I notice? Well, if I take any pair of elements, every pair of elements is in a 3 circuit and a 3 co-circuit. Okay, so here's 1, 2. What's the circuit it's in? It's in 1, 2, 3. So that's the circuit. What co-circuit is it in? It's in 1, 2, and 10. There's a co-circuit. All right. And I can do that for any, there's nothing special about choosing 1, 2. I can choose any consecutive, I should say consecutive pair. Sorry, I should say consecutive pair in the ordering. All right, so if I take a consecutive pair in the ordering, then those two elements are both that consecutive pairs in a circuit and a three circuit and a 3 co-circuit. And I can do that for every pair of that circular ordering. So as a corollary, although maybe not a corollary, but because you got the first result, if you get the second one for free, because certainly if I've got 2 consecutive elements in a 3 circuit and a 3 co-circuit, that means every element's in a 3 circuit and a 3 co-circuit. So maybe it's corollary might even be a bit strong. Observation maybe not even that. You must be a wheel or a whirl. All right. So what about this time? We consider matroids? They've got a cyclic ordering such that if I take t minus 1 consecutive elements, those t minus 1 elements are in both a T circuit and a T co-circuit. All right. So I'm interested in this property, matroids with this property. So matroid M has the cyclic T minus 1 T property. If there's a cyclic order of the ground set, such that every T minus 1 consecutive elements of the ordering is in a T circuit and a T co-circuit. So we've seen wheels and of course whirls work like that as well. What about other ones? Well, we'll go back to our spikes. Do they do it? Remember, spikes have the property that every pair of elements is in a 4 circuit and a 4 co-circuit. But now I want to do an ordering. All right. And here, so if I do the ordering, there's an ordering. If I take any 3 consecutive elements, 1, 2, 3, that's both in a circuit, a 4 circuit, and a 4 co-circuit. So 1, 2, 3 here. The 4 circuit involves 1, 2, 3, 4. And the 4 co-circuit also involve 1, 2, 3, 4. Right, I could do that for any 3. Okay, so spikes have the 3, 4 property. But are there other examples? They're beyond spikes and wheels and whirls. And you can have swirls. So this time what I'm going to do to get a swirl is, here's a rank 5 swirl. Take a basis, rather than blue elements. Oh, better label the basis. And now on the line spanned by B1 and B2, add 2 points. On the line B2 and B3, add 2 points, B3 and B4. And if I delete, the basis elements, I get a swirl, right? And there's a rank 5 swirl. And if I label those elements I also have the property that every consecutive 3 is in a circuit, and every consecutive 3 is in a 4 circuit, and every consecutive 3 is in a 4 co-circuit in exactly the same way. One thing to notice here is that in this case the orange and the blue coincided, 4 circuit and the 4 circuit coincided for the 3 element set, the green set. If I go back one slide, or 2 slides. For the wheels and the whirls, the circuit, the 3 circuit and the 3 co-circuit weren't the same. All right, one went forwards and one went backwards. So here's, we've already seen wheels and whirls have the 2-3 property. Direct sums are 1-2, they are 1-2 cyclic. All right. So, but more importantly, wheels and whirls are 2-3 spikes and swirls are 3-4 cyclic. And there's the definition of a rank R swirl, but the picture I drew is exactly what I've said, and that's in that bit of blurb. So what can we say about matroids with this property? So this in the same Creswick meeting, Nick Patel, Deborah Chan, Tara Five, myself, it's a theorem resulting out of that meeting, the Creswick meeting a couple of years ago. So M's a matroid, you've got an ordering, there's a cyclic T-1 T ordering, then provided n's at least 6T-10, so there's our sort of so bound, but we can actually, I'll say a bit more about that a little bit later. And T's at least 3. What can we say about those guys? Well, first thing, n has to be even, so the ground has to be even. For the consecutive T-1 in the ordering, the T circuit and the T co-circuit is unique. All right, so there is only one T circuit and T co-circuit that has that property. If you go back to, maybe it's easier set for the wheels and the whirls, they are unique. All right. Once you've got enough elements is not large. What's enough elements? 8 elements in your wheel or your whirl, then they are unique. The consecutive pair is only in one 3 circuit and one 3 co-circuit. There are no others. All right. That's the first thing, but then there's the parity condition. All right. So wheels and whirls are odd in the sense the parity condition there at T is 3. Spikes and swirls are even, the parity conditions on them because T is 4. So let's take a consecutive, I don't know, 5 consecutive elements. Is that what I want to take? So now I'm a little bit. T is odd, but I can take 4 consecutive elements. That would be a mistake, take 5. I want T to be odd. Let's take 4, better correct that. If I want T to be odd, so I'm looking at 4, 4, 5. All right. When T is odd, right. So if I look at the next consecutive 5, take the 4 plus 1, that's either a T circuit or a T co-circuit, but it can't be both. T is odd, so it can't be both. So if you go back to the wheel and the whirl, if I go forward 1, that was either a circuit or a 3 circuit or 3 co-circuit, but it can't be both. It can't be both. That's the first thing. The next thing is, if that was the orange one, if those 5 consecutive elements is a T circuit, in this case a 5 circuit, then my co-circuit, you go back 1. So the co-circuit containing the 4 green will be, you go back 1. So they sit like that. And then the other thing when T is odd is that the circuits jump 2. I've jumped too many, haven't I? 1, 2, 3, 4, 5. Yeah. Let's fix that up. All right, there's the circuits. And similarly, the co-circuits jump 2 as well as you go round. Right? So that's what happens generically if T is odd. If T is even, think about swirls and spikes. Remember, they coincided, the circuits and the co-circuits coincided. So if T is even, so let's do, so there's my consecutive 5. So this could be a 5-6 ordering. Then one of these, that, or the one going backwards, is a circuit or a co-circuit. Exactly, oh sorry, one of those is a circuit. Not both of them, only one of them could be a circuit. So let's say it's the first one. Yeah, too big. Okay. So let's say it's the first one. The next thing is, if the orange is a circuit, then one colour, but that'll do. There's my co-circuit. All right. That's my co-circuit. And then they also jump in 2s. So the next circuit, I'm going to have, get this right, colourings is, that's my next circuit jumps 2, and the next circuit after that jumps 2 more. All right, so there's a parity condition on that. And similarly for the co-circuit, so the blue's got to coincide with the, so that'll be a co-circuit, and that'll be a co-circuit. And that'll be all the circuits in the co-circuits. That's there. So that's what that slide says. So you don't need to read that. That's what we've just been talking about. And that's what the second slide said for the even, of how the circuits and the co-circuits work. They work very much, they generalize like spikes and swirls for even, and wheels and whirls for odd. The bound is tight for T equals 3. All right. But what about tighter bounds for other values of T? So if I go back, so in recent work with Jerry Toff, there's a PhD student of Nick's and mine. Jerry's actually got this bound now down to ends at least 4t minus 5. All right, so he's got this bound down to 4t minus 5. So when t equals 3, that means it ends at least 7, but since n has to be even, you still get n is at least 8. All right, so for t equals 3, it coincides, but that's getting back down, bound down a bit. How much tighter we can get that, I'm not sure. All right, I don't know if you could actually say explicitly what that lower bound would be. That's currently what we've got for that. And then you might say, given the ordering, why don't you consider T-cyclic matroids? So these are matroids motivated by those last results. So it's the cyclic ordering, such for all odd I, that's either a T circuit, and you move along 1, so you just permeate it one step, and that's T co-circuit in the ordering, and that's odd. So think of wheels and whirls, and the even one. So your even T cyclic, if the T circuits and the T co-circuits coincide, so your spikes or swirls. Right. So here's one, a 3 cyclic wheels and whirls, so that the T circuits and the T co-circuits are offset by 1. The spikes and swirls, the T circuits and the T co-circuits coincide. If M has at least enough elements, then and you've got the T minus 1 T cyclic property, all right, then you must be T cyclic. All right, that's now 4T minus 5. in your T cyclic. Is there anything we can say about those structures? And the answer is yes, and they give rise to flowers. So a little bit of taste for the people at the Matroid audience who know a bit about flowers. And based on those orderings, I can concatenate the subsets so that the least size, in this case, T is greater than 3 and odd. T is at least this size, T minus 1. So in the 3 case, I can put these petals into sets of size 2, and then you always generate what's called a T daisy. All right, so I'm running out of time, so just for those who know what a T daisy is, and I can generate a T daisy. The consecutive petals, that's the local connectivity. For non-consecutive, it's half T minus 3. All right, and if you put T equals 3 in, so for wheels or whirls, the local connectivity, for consecutive petals, the local connectivity is 1. For non-consecutive petals, it's 0. If T was 3. Why do you need T to be at least 3? Because if you're one cyclic, you're actually a one anemone. All right, because you are going to consist of half the elements will be loops, half the elements will be co-loops. You put an ordering, so it's loop, co-loop, loop, co-loop, loop, co-loop. There's an ordering, and that will give rise to a one anemone. What about even? The same idea applies, but this time, strange things happened. The local connectivity is a half T minus 2. Okay, it's half T minus 2 for all consecutive petals, but I haven't said anything about here whether it's a daisy or an anemone. All right, and if you go back to the spikes, our favourite example on spikes, that's an anemone. The petals are, petals is these. Probably got petals too small. Oh no, I can have T minus 2. Here's the petals. All right. And in some sense, the ordering doesn't matter there, so that's an anemone. The ordering does matter here, so that's a daisy. And so you can get both. All right, you can get both right when T is even. A little caveat there, if T is 2, you only get 1 anemones. But if T is at least 4, there exists T minus 1 anemones and T minus 1 daisies. All right, so you get both when T is even and at least 4. And the last thing I want to say is, this is work with Jerry and Nick. Jerry Toff, PhD student Nick. What about for ST cyclic? So if there's a cyclic ordering, so E minus 1 consecutive elements in an S circuit, T minus 1 consecutive elements in a T co-circuit, what can you say about that? And the only thing I'm going to say here is, because I have to say it for another day, T cyclic Matroids generalize to TST cyclic, so that's all fine. And you can have constructions for building these ST cyclic for arbitrarily large S and T. All right. And the constructions involve quotients and lifts. All right. And actually, all of this work, these constructions of these bigger ones, involve quotients and lifts from smaller ones. You can keep building these things up using those operations. All right. So I'll finish there, Rose. So I'll leave it at that.
Thank you. Sorry, there's someone talking in the background, but thank you. And we haven't been doing applause because it's difficult to get everyone to unmute at the same time, but thank you. All right, so now is a good time for questions. So something that I wanted to ask, which is, you mentioned the constructions of these ST cyclic matroids, and that if you have matroids where every L elements is in a T element circuit and a T element co-circuit, there's only finitely many if what L is less
If
than 2T,
L was
you said, or
less than
something?
2T.
Right. And so I was going to ask, do you know if
There's
constructions in
conditions
general?
on these. Yeah, I should say there's conditions on. Yeah, I've been. What I've said is not. I've got to add extra technical details to get things right. So you've got to have a certain number of elements and things like this for this thing to work, and stuff
Right.
like that.
I guess what I was wondering is, like, if there are finitely many, are there always at least one? Like, you have constructions.
Is there at least one for when they're a finite number? When I was doing writing the talk, and I was wondering about the U24, and I was wondering, I was actually looking at that particular one, and up till yesterday, it had none. And then I realized, oh, U24 is actually one. My better thing was proof by example and pick some combination where it was actually none. But then I realized I get U24, ding, So that ruined that. But I don't know of any of none. I suspect if the small ones you probably thought hard enough, you probably might get none of them.
That's not something that I have experienced.
Okay. Yeah.
The base case for these ones are uniform. ST cyclic, so a class of where these ST cyclic ones arise would be uniform matroids. Yeah.
Right. Thank you.
Sorry, what was the question?
All right. Are there any other questions? All right. Thank you again, Charles.
Right. Thanks, Rice.